All right, in this explainer, we're going to dive into a really core concept in algebra, polynomials. And hey, forget any of those dry, boring math lessons you might remember. We're going to look at this like we're composing music, something that's actually creative, structured, and yeah, even beautiful. Let's kick things off with this fantastic quote from the mathematician G.H. Hardy. A mathematician, like a poet or a painter, is a maker of patterns. And that, right there, is exactly what we're about today. We're not just crunching numbers, we're learning to see the elegant, logical patterns that make up the language of math. So, let's just run with that idea for a minute. What if algebra was less like a dreaded test and a whole lot more like a symphony? A grand arrangement where every single part has its place, and they all work together to create something amazing. That's the lens we're using today. Let's start our first movement, the algebra symphony. We're going to see how polynomials are pretty much math melodies, these cool expressions that combine different mathematical pieces in really harmonious and predictable ways.
Okay, so every great symphony has to start somewhere, right? It starts with a single foundational note. And in the world of polynomials, we call that single note a term.
So what exactly is a term? Well, it's one of the most basic building blocks you can get. It can be just a plain number, like 5, or it could be a variable, like x, that mystery value we're always trying to figure out. Or it can be a number and a variable multiplied together, like 2x. Each one of these is like its own single, complete musical note.
Now, here's where it gets interesting. How do we tell these notes apart? Like, how do you know when one term ends and the next one begins? Well, the secret is actually super simple. You just look for the plus or minus signs. They're the separators. So 2x by itself, that's just one term, a single note. But in 2x plus 3, that plus sign splits them apart, giving us two distinct terms. And if you have 2x plus 3 minus y, now you've got two separators, which means you've got a melody of three terms. It's really that straightforward. Okay, so we've got our individual notes. Now, let's see what happens when they start playing together. We're moving from a single soloist to a duet, maybe even a full trio. And this is where we get the different types of polynomials. And just like in music, when you arrange these mathematical notes together, you create something brand new that gets its own special name. It all comes down to how many terms are playing together in harmony. First up, we've got the monomial. Just think mono, it means one. This is our soloist, a single term taking center stage. Something simple like 2x is a perfect example. Next, let's bring in another musician for the binomial. Bi means two. Think bicycle, right? Two wheels. So this is our duet. It's made of two terms joined by a plus or minus sign, like 2x plus 3. Two distinct notes playing together. And I bet you can guess what's next. Yep, the trinomial. Tri means three, like a tricycle. This is our trio, creating a richer sound with three terms all playing together, like in 2x squared plus 3x minus 2. Monomial, binomial, trinomial. Soloist, duet, trio. See how the pattern just builds on itself? All right, let's switch up our analogies just a little bit. We've talked about how many terms are in the band, but now we need to talk about their power. We're about to get into the polynomial power ranking system, which we officially call its degree. So in our algebra symphony, not all notes have the same oomph. Some are louder, more powerful than others. You can think of each term as having a royal rank, and that rank is all about its exponent. And here is the absolute key takeaway. The degree of the entire polynomial is just the biggest exponent you can find in any of its terms. You don't add them up or anything complicated. You're just on a mission to find the single highest rank in the whole expression. Let's look at this chart to really see it in action. So take 2x, you don't see an exponent, but there's an invisible and implied 1 hanging out there with the x. So that's a first-degree polynomial. Now look at 2x squared plus 3x. We see an exponent of 2 and an exponent of 1. What's bigger? The 2, of course. So it's a second-degree polynomial. And finally, in 2x cubed minus x squared, the largest exponent is clearly 3. So it's a third-degree polynomial. You just find the highest number. Okay, we've got one last key player to introduce today. Every army needs a general, right? Every orchestra needs a conductor. Well, in a polynomial, we call this the leading coefficient. It's basically the expression's commander.
Now, the definition here is super precise, and this is really important. The leading coefficient is the number in front of the variable of the first term. But, and this is a big but, only when that polynomial is written in descending order of exponents. You have to line up your musicians from the highest royal rank all the way down to the lowest before you can figure out who the leader is.
So let's make that process crystal clear. Here are the steps. First thing you do, arrange all the terms from the biggest exponent down to the smallest. Got it? Okay. Second, you look at the very first term that's now leading the line. And third, the number part of that specific term, its coefficient, that's your commander. All right, let's try it out. Take a look at this polynomial, 2x cubed plus 3x squared minus x plus 2. First step, check the order. Are the exponents going down? Let's see. We've got a 3, then a 2, then an invisible 1. Yep, it's already in perfect order. So who's the commander leading this charge? It's 2. Because the polynomial was already arranged correctly, all we had to do was look at that very first term, 2x cubed. The coefficient, that number right out in front, is 2, and that is our leading coefficient. Simple as that. So, after all this, you might be wondering, why does this matter? Terms, degrees, coefficients, what is the big picture? Well, it's that you are learning the fundamental grammar of mathematics. These aren't just a bunch of random rules. They are the principles that let us build and understand really complex ideas with perfect clarity. Let's just quickly recap the big ideas from our little symphony here. Terms, those are the individual notes, our basic building blocks. Polynomials combine those terms to create our math melodies. The degree tells you the overall power, the royal rank, of the whole expression. And that leading coefficient, that's the conductor, the leader of the entire operation. And that brings us right back to where we started. Remember, a mathematician is a maker of patterns. So now that you know the rules of this symphony, the grammar of this mathematical language, I'll leave you with a question. What new patterns are you going to start to see?